data-driven surrogate modeling and sensor actuator placement framework for flexible spacecraft. Authors Matthew Hilsenrath, Dr. Daniel Herber, presented by Matthew Hilsenrath. This presentation will deliver an introduction to the problem, truth model and simulation data, dynamic mode decomposition surrogate modeling, Hankel equivalence, optimal sensor actuator placement, and results. Introduction. Flexible spacecraft exhibit tightly coupled rigid body and elastic dynamics, high sensitivity to disturbances, and stringent mission constraints that complicate modeling and control. Classical, analytical, and modal modeling approaches can capture dominant dynamics, but often become impractical for high-dimensional nonlinear systems. Traditional control strategies rely on fixed modal models with controller augmentations such as input shaping with proportional derivative control or model predictive control for handling actuator limits and disturbances. Data-driven methods enable dynamic models to be identified directly from simulation or flight data, avoiding explicit modeling of underlying physics. Recent work demonstrates promise for predictive control of flexible spacecraft using data-driven reduced order models. Most existing approaches assume fixed sensor and actuator configurations, neglecting how hardware placement alters system dynamics and model validity. Classical analytical solutions provide a baseline for validation, but may lose accuracy as system dimensionality, nonlinearity, or configuration complexity increases. Changes in sensor and actuator mass, location, and configuration can invalidate analytically derived models or degrade controller performance. The proposed framework iteratively updates reduced order models and hardware placement, enabling direct comparison against and improvement over fixed analytical solutions. Truth model and simulation data. A nonlinear simulation of Euler-Bernoulli beam theory was designed to model flexible spacecraft appendages. The simulation was developed to model the first 10 vibration modes of the cantilevered solar array. Points on the beam are discretized into a mesh of nodes. The simulation captures position with respect to the fixed spacecraft body from the superimposed vibrations, making this time domain dataset available for data-driven analysis. This model is regarded as truth to establish a baseline by which data-driven surrogate models may be contrasted with. Shown below are the parameters used to model the first 10 vibrational modes, and a plot of each of the first 10 vibrational modes plotted independently in the same figure. Surrogate modeling via dynamic mode decomposition. The analytical truth model produces high-dimensional time series data. The data are a mesh of points representing the physical locations on the structure and the time history of movement of the point. An appropriately chosen low-dimensional surrogate model is the intended output. Data-driven methods will be employed to determine this model. The surrogate model has a known analytical solution. Therefore, a comparison can be made between the surrogate model and its analytical solution, and observations can be made about the fidelity of the data-driven modeling technique. Furthermore, the data-driven technique lends itself directly to a known optimization routine, yielding a novel approach. Dynamic mode decomposition is a data-driven algorithm that identifies the spatiotemporal coherent structures from complex and nonlinear systems by approximating them with a high-dimensional linear model. Dynamic mode decomposition can be carried out by aligning node positions into vectors x as a time series. Then the vectors can be aligned into two time-shifted matrices, x and x prime. These two matrices, x and x prime, can be related by a best fit linear operator, A, to move each of the high-dimensional vectors one time step into the future, such that x prime is the product of A and X. For translation waves and evolving systems with distinct modal characteristics, this routine is sufficient. But for standing waves, it has been noted that the process fails to identify the underlying system. This shortcoming can be overcome by extending the state space by yet another time step, such that the time-shifted matrices are X and X prime, as shown below. Once again, these matrices can be related by a best-fit linear operator, high-dimensional vectors one time step into the future, such that X prime is the product of A and X. This preserves and isolates the modal structure of the standing waves. The determination of A may be as trivial as producing a pseudo-inverse of X and solving X prime X transpose equals A. For the data-driven methods, the row space of X may be in the tens of thousands or more, and the column space will be nearly as long as the number of time steps, typically less than the row space. For the identification of standing waves, the row space doubles. This computation is not practical. We can subvert the dimensionality problem by projecting the X operator into a low-rank subspace using singular value decomposition. We compute the reduced singular value decomposition as shown below, where the subscript R is showing that we are retaining only the leading R singular components. The low-dimensional approximation of A is then given by A tilde. The selection of R requires recognizing the truncated energy inherent in each singular value. The plots below show the singular values, as well as the cumulative sum of the singular values, which are representative of the energy in the system. The selection of 6 singular values shows significant energy, and by analyzing the cumulative singular values, we can see that the system reduced to 6 states, or 3 complex conjugate modes, captures greater than 99.95% of the energy of the system. The eigendecomposition of the reduced order modal matrix A tilde yields the dynamic mode decomposition eigenvalues lambda and eigenvectors W. The corresponding dynamic modes in the original state space are given by phi, where each column of phi is a dynamic mode, and each eigenvalue, lambda, governs its temporal evolution via lambda t. Defining initial modal amplitudes, the time evolution of the system can be reconstructed as shown below. The lower order surrogate model is meant to capture dynamic behavior associated with the first 3 mode shapes. The truth model of the mode shapes is shown at right. The dynamic mode decomposition reconstruction capturing the first 3 shapes is plotted against the truth model, capturing the full 10 mode simulation below. Frequency domain analysis of the dynamics shows agreement between the truth model and the dynamic mode decomposition reconstruction. The truth frequency inputs and the extracted dynamic mode decomposition frequencies are in alignment via the vertical dashed lines. The normalized amplitude fast Fourier transform of the truth model and the dynamic mode decomposition time domain reconstruction line up in the main plot of the figure. Data-driven and Gramian product Hankel equivalence. For optimal sensor actuator placement, we first define a balanced representation of the controllability and observability gradients. We aim to show that balanced observability and controllability gradients can be produced for a linear time invariance system for the data-driven Hankel matrix. By virtue of the distinct mathematical objects, these gradients will not be identical. The balanced realization is achieved by proving the spectral composition is the same. To produce this proof, consider a discrete time LTI system in state space form. Next, we can define the Markov parameters, also known as the impulse response matrices, by H, which are the discrete time output samples in response to an impulse input at time 0. These samples are arranged into a data-driven Hankel matrix, as shown below. If we look at the structure of the observability and controllability matrices, and furthermore, their product, we arrive once again at the impulse response matrix, which is the Hankel matrix. The infinite horizon observability and controllability gradients, WC and WO, are related to the Hankel matrices by the Hankel matrix product with its transpose, the Hankel matrix transpose product with the Hankel matrix. By properties of the singular value decomposition, the non-zero singular values satisfy the property below, showing the equivalence of the spectrum. Therefore, the Hankel singular values converge to the balanced realization of the controllability and observability gradients, WO and WC, which are the eigenvalues of these gradients produced strictly from data. Optimal sensor actuator placement. The Maghami-Yoshi cost function is employed to optimize the sensor actuator placement. This cost function maximizes the intersection of system controllability and observability subspaces for optimal sensor actuator placement. This Hankel matrix can be constructed using positional data from all points X on the simulated solar array. For sensor actuator placement, we wish to select discrete locations which align the controllability and observability subspaces. Our goal is to select a set of sensor locations from a set of candidates, C, to ensure the locations capture the most dynamic information about the system and have the most control authority over it. So the cost function is modified to utilize the Hankel matrix of data from candidate locations. HC are the singular values of the Hankel matrix for candidate sensor actuator location set C. This penalizes small singular values and ensures large singular values are utilized to capture the most independent dynamic content. The cost function was evaluated over the exhaustive search space to ensure a global minimum was found. For higher order, higher dimensional problems, this approach may not be possible, but the study at hand is not concerned with optimal search space strategy. As we see below here, the optimal candidate locations are right next to each other on the tip of the solar array. And that's also identified in the minimum values of the objective function on the right. Placing the sensor actuator pairs based on the initial optimal locations fundamentally changes the dynamics due to the inertia of the sensor actuator added at that location. A modification to the dynamics is facilitated by employing the ANC equation from Wu and Lin, which is shown below. The subsequent iterations converge on the optimal placement by evaluating the cost function with altered dynamics based on sensor actuator placement. Utilizing the dynamics modification to account for sensor actuator placement, the data-driven cost function was evaluated over the search space and iterated until subsequent iterations yielded identical placement, indicating convergence of an optimal placement. You can see the minimum locations, the minimum cost function for the locations in red and blue, the objective function value plot, and the actual locations on the solar array plot to the left. The results. The overall intent was to prove a method that is scalable to highly complex systems which may not have analytical solutions for sensor actuator placement methods. Since the control, B, and observation, C, matrices, are derived from a balanced realization, verifying results in a controller implemented on the system is sufficient to demonstrate performance of the optimized system. The sensor actuator placement was implemented in an LQR optimal control scheme set to null vibration response, and results proved that the optimized locations required the least energy and showed the best time domain performance. The LQR was constructed with the intent of suppressing the vibration loads intrinsic to the solar array. The vibration suppression objective was achieved through recasting the modal formulation into a linear time invariant system such that modal dynamics were preserved and represented. Since B and C were selected via Hankel-based optimization, the closed-loop system was expected to suppress vibrational modes with the minimum energy output. In contrast, when suboptimal placement is enforced, the control input or resulting feedback degrades vibration suppression. The time domain performance shows measured displacement over time at the sensor actuator locations. The open loop system responds with passive damping. Suboptimal placement system has a controlled response, and the optimal system has a controlled response with less overshoot and lower settle time. The response power spectral density shows, visually, less area under the curve for the optimal solution, and thus a lower energy output to produce the system response. The overall system performance results are shown below. We can see that for variance from the spectrum, which is the integrated PSD, overshoot percentage, settling time, and integrated control effort, the optimal placement has greater performance than suboptimal or open loop in any of the applicable realms. Thank you all very much.